Hello, it's Keith here, and this is lesson 4 of the so-called ChibiTracks tutorials of my 6502 assembly programming tutorials. Now, we're looking at the final part of ChibiTracks, my music player. What we're going to be looking at today is the tone calculation routines that do the fractional tone calculations. Let's go to the source code and I'll be able to explain a little bit better. So basically, we have for each system an octave lookup table that looks something like this. However, this is only for the pure tones E, F, G, A, B, C, so on. So if we want a sharp or a flat, we have to basically take two values and divide them by 2, and that will create a sharp or flat. That's all very well and good, but there is another thing. Well, what if we want to do something a bit more subtle? Maybe we want a sort of slight waving tone, or maybe we want to slide from one note to the next. That's not going to be enough, is it, to do that? And so what we've got is the ability to do fractions of tones. So we've got 16 steps between even that sharp and that regular tone. So that's what the code we're going to be looking at today does. We're going to be looking at how I've done it, and we'll see how things are being calculated. So basically, we've got a function called tween tone that is run by the music software, and this will select a tone based on two things. The first thing is the contents of the E entry in the 0 page. This is the tone number. Now this includes the sharps and the flats, so each of the values here would be 0, 2, 4 and 6 and so on, with the 1, 3 and 5 being the in-between sharp or flat notes. Sharps and flats are effectively the same thing, just in opposite directions, if you see what I mean. So the calculation method is exactly the same there. So basically what we could do though is, as well as the E register, we have the accumulator, which has an offset. Now the top nibble is a whole number offset, which is simply added to the E register, but the bottom nibble is a fractional offset, which is basically a value of 0 to 15 between the two notes. So if that fraction is enabled, we will get a note and its neighboring counterpart, and then we will calculate a fractional part between the two and return that. And this is how we are able to make wavering notes or slides, and as I say, that's something we might want to do. The ChibiTracks and ChibiSound Pro software doesn't support things like envelopes, so if we want to make a note that kind of flutters or waves, we do have to use this fractional code to do that. Now, the code that calculates a tone is the getChibiTone function. So this will basically calculate a note within the lookup table. It will calculate the sharp and the flat. But then if we want to combine two and use these fractional offsets, the bottom nibble here, what we do is we will get the first tone with getChibiTone here. We get the second tone here. The first one will be stored in HL and the second one will be stored in DE, and then we use the tween tone function here to get the offset between the two, as I say, with a value of 0 to 15, with 0 being the whole of HL and 16 being the whole DE, and anything in between being a fraction of the two. So this is creating a smooth scale of 16 steps between those two absolute values. Now the getChibiTone function itself, basically what this is doing is it's loading the HL entry in the 0 page with the Chibi octave, which is this table here. There is one for every single platform that I can play the music on, which is pretty much everything in my tutorials, I think. So we're using that, and then what we're going to do is we are going to use the E entry in the 0 page as an offset. But the bottom bit is the sharp or the flat function. As I say, it's basically the same thing. So we are zeroing that, which is convenient because each entry in that table is 2 bytes. So that is effectively multiplying the entry number by 2 there, and we're adding that to the HL table. We're loading the first byte and storing it in E, and then loading the second byte and storing it in D. So we've got our DE pair here. What we're doing next is we're checking that bottom bit. Now that is the sharp flat function. Now if that is 0, then actually we've got all we need. We only need the one value. It's the correct value, and so we at that point we'll just return. So we're jumping down here and returning. Now if we do need that sharp function, what we're then going to do is we are going to basically halve the value in DE, and we're going to get the next value along, and we're going to store that in H and L, and then we're going to halve that value, and then we're going to add the two together, and we're going to swap DE and HL. DE and HL are both 0 page entries here. They're mimicking the Z80 registers because this was ported from the Z80. This command here will swap DE into HL quickly. We've got it here. It's just using the X register as a temporary store, swapping D and H here in the 0 page, and then E and L in the 0 page here. It's just something I'm doing there to get the final value into DE basically here. And so this is the function that we're using twice here. The first time we're getting the value in HL, the second time we're getting the value in DE, and then we are using the tween function to combine the two. So this tween function is doing the combination of the two. So how does that work? This tween 16HL DE function will basically take a fraction of the DE part and a fraction of the HL part and add them together. Now the amount of the DE part is the value in the accumulator. So if the accumulator was 1, it would take a 16th of the DE part, and it would then take 15 parts of the HL part. And so basically if the accumulator is 0, we're literally just returning HL. And that's why we've got to check here that if the accumulator is 0, we're simply returning, because HL is already the entire value that we need. Now what we're doing here is we are running the function the first time with the accumulator set the way it is, and then we're flipping that and we're subtracting it from 16 to get the fractional part that we need to take from the HL part second. So in both of these cases we're running this function, and it's going to take a percentage of HL based, and it's basically the function HL equals HL times A divided by 16. And so if A equals 16, we will get the whole of HL, and if A is 0, we will get absolutely nothing. And you can see here, our first check here is if the accumulator is 0, we are effectively returning. Now in this case we've actually already got that check up here, so we would never actually run this, but I've made this in a way that can be reused because I think this will be useful in other cases. So if the accumulator is 0, we're effectively going to return 0, and so we've got this check here to see if the accumulator is 0, and in that case we're simply going to 0 HL and return. So that is so that we don't need to do any work. Now actually that will never really be run because we've already got the check up here to see if the accumulator was 0 anyway, and in that case we're simply returning. But I thought this code would probably be useful in the future, so to make it future proof I've put that check in there. Now if the accumulator is 16 or greater, which again it never actually will in the way I'm running it here, but for future proofing, then in that case we would actually just want to return the whole of the HL value. As I say, 16 divided by 16 would be HL times 1, which would just return HL. So in that case we're simply returning. In any other case we actually want to do some fractional division there. So what we're basically going to do is we are going to 0 HL, and we're going to store what I'm going to refer to as the build-up in HL and the fractional part that we might want to add for each bit of the accumulator in DE. So basically what we're going to do is we're going to repeatedly divide the original value in HL, which is now in DE, by 2. We're going to test the matching bits in the accumulator, and if the matching bit is 1, then we're going to add the value in DE to HL, and over 4 iterations this will basically mean that we've basically done this calculation here. So what we're doing here is we're dividing DE by 2 here, and so this is effectively halving it, and then we are testing the bit 3, which is the equivalent to the value of 8 in our accumulator. Now if that is 0, then we're just skipping the next part, but if it's not 0, what we're going to do is we're going to do one addition using this add HL DE function here, which will add the 0 page DE pair to the 0 page HL pair. What we're then going to do is we're going to shift the bits to the left, so the old bit 2 will become the new bit 3, and we're masking that, keeping only the bottom 4 bits. And once all of those bits are 0, then we're actually finished. This might take 4 iterations if the bottom bit 0 was 1, but if, for example, only the top bit, the bit 3, was 1, then this would only need a single iteration, which is why I'm doing that masking there as my loop counter. I could have used a count of 4, but in some cases that would have been slower. So we're repeatedly shifting so that we can do the same bit 3 test each time, but because we've bit shifted to the left, each successive bit 3, bit 2, bit 1, bit 0 will have half the weight of the previous bit, and so each time we are halving the value in DE and we're adding half that value if the matching bit that's tested is 1. And so by doing this we're effectively doing this calculation here, but hopefully a little bit more quickly than if we were doing repeated adds or some other kind of function. I think this is probably about the most efficient way of doing things. Certainly on the Z80, maybe a little bit slow on the 6502, but it's certainly the fastest way I know of doing this kind of multiplication or division. This is kind of a combination of multiplication and division, but as I say, this is designed to basically pad out a lookup table. I had another sine table function where I had a sine table of just 16 entries, but I actually wanted 256 entries. And again, this function will be ideal for that, because you can create 16 steps between your two entries in your lookup table, and you can multiply up your 16 entries by 16 fractions and give you a 256 entry lookup table, which is, as I say, why I think this will be useful again. But as I say, in the context of the example code, the ChibiTracks code, it is used for creating the sounds, the byte data that needs to be passed to my ChibiSound Pro sound driver, which actually creates the tones, and it's used for the fractional tones, calculating sharps and flats, and doing the wavy notes. Well, as I said before, you can go to my website, download the source code, the build scripts, and all that kind of fun stuff, and you're welcome to do anything you want with it. You can also download ChibiTracker Pro, the Windows-based music tracker, which is only a basic little thing, but it's what I use to create the music, and it's what I'm going to use for my future music needs, because that's how we make these things get better. Anyway, I hope you've enjoyed what you've seen today. Go to the website, download the build script, source code, and that kind of stuff. Have some fun with it, and as I always say, you're welcome to use it in your own projects, even if they're commercial. You're welcome to do that. Thanks for watching, and goodbye.